Electron configurations and the periodic table is what we've all been waiting for. Valence electrons, which I believe we mentioned earlier, but didn't really talk too much about. Valence electrons are the electrons that are in the outermost principal shell, the highest principal shell, the highest floor in the hotel room, in the hotel. So how many electrons are on the highest floor? How many have the highest principal quantum number n? These electrons are important because they're involved in chemical bonding. Remember, we compared the 1s orbital and the 2s orbital, and the difference was in energy but also in size. The 2s was larger. So as you go higher, 2s, 3s, 4s, 5s, those electrons can be more on the outside of the atom. The electrons are involved in bonding, and it's the electrons on the outside that are most involved in bonding. The ones in the inside are called the core electrons. So those are the ones on the lower levels. They don't do much. They just sit there. It's like, hey, we got a good deal in this room. We're keeping it. We're not going to mess around. So looking at an electron configuration, we can identify the core electrons and the valence electrons. So here's the electron configuration for silicon. 1s2, 2s2, 2p6, 3s2, 3p2. 2 plus 2 is 4 plus 6 is 10, and 2 is 14. Silicon is element number 14. 14 electrons total. The valence electrons are going to be those with the highest big number. So 3s and 3p. That's the highest floor in the hotel that has people staying in it. So however many people are there, however many electrons are in that highest principal shell, those are the valence electrons. So here it's 4, 2 and 2. And the rest of the electrons in the lower levels are called the core electrons. We also learned that we can read this off the periodic table because for silicon it's in group 4A, and so it has 4 valence electrons. Let's write an electron configuration for chlorine and identify the valence electrons and the core electrons. So chlorine has 17 electrons. So 1s2, 2s2, 2p6. There we've got 10 electrons taken care of. 3s2, 3p, so 2, 10, 12. We need 5 more, so it would be 3p5. So in this electron configuration, which ones are the valence electrons? These guys with the 3s. Okay, so those are the valence electrons. And which are the core electrons? The rest of them, right? Those are the core electrons. So compared to writing the electron configuration, that seems pretty easy, right? We're looking at the highest, and it's not just the 3p5, it's all of the 3s. Okay, so whatever the largest number is here, all in those, whether they're separated by other things or not. We're just looking for the highest big number, and then we're going to count all of them. Selenium. Here's the electron configuration for selenium. And here we get the skipping around business, the 4s2 and the 3d10, and then 4p4. The highest occupied energy level is the 4. Only the electrons in the 4th level count. So these 3d10 electrons don't count as valence electrons. So we've got 2 here and 4 there. So selenium has 6 valence electrons. Those in the 3d are considered core electrons. Does that make sense? Yes?
It makes sense, but at the same time not, because if they're higher energy than the 4s, why?
Why? Yeah. That's a very good question. The 3D fills after the 4s because it's higher in energy. So why would this not be a valence electron? It fills, it really gets complicated when you dig in very far. The reason that this is higher in energy is because of interactions between the electrons that are way beyond the scope of this class. But these electrons belong to this lower principal shell. When those orbitals are empty, the 3s, the 3p, and the 3d all have the same energy level. So for like hydrogen only has one electron. All these orbitals are still there. In the hotel, the rooms still are there even if people aren't staying in them. What happens with when they get filled up is that the interactions between the electrons cause the energy levels of them to shift a little bit. So I'm afraid that's the best explanation I can give to you. But it doesn't make a lot of sense. I agree with you. You just kind of have to accept it, yeah. When we count valence electrons, whatever the highest principal quantum number is, so here it's 4, we only count the electrons in that level. So elements in the same column of the periodic table have the same number of valence electrons, and they also have similar outer electron configurations. So this is the first, second, and third rows of the periodic table. And there's this little gap here because normally there's a big gap there. So imagine cutting it and splitting it apart and so that to make room for the transition metals. But we don't need to do that because we're not looking at those. Do you see a pattern here? So here's hydrogen, and it's in the first row, and so it's 1s, and then over here is helium, so 1s2. Here we've got 2s1, and the next electron goes into the 2s2. And then here are 6 boxes, and 1, 2, 3, 4, 5, 6 electrons. So boron, we add 1 electron, we get carbon. We add 1 electron, we get nitrogen. We add 1 electron, we get oxygen. And so their electron configurations are just going up by 1 on that last subscript. You see that? And so after we fill up the second level, then we go to the third level. And there's sodium and magnesium and aluminum through argon. If we look going down, what they're showing you here is the highest, the last term in the configuration. Just the last term. Well, they're showing you the valence electrons, I'm sorry. They're showing you the valence electrons. So for hydrogen, it only has 1 electron, it's a valence electron. But lithium, the valence electron is an S1 and S1. And the thing that's changing is the principal quantum number. Here, beryllium and magnesium, 2s2, 3s2. For boron and aluminum, the configuration here is the same except that the number's bigger because they're filling a larger, the next highest level. For looking at it like this, it would actually be nice to have helium over here. If we stuck helium over here, because he would be 1s2 and fit into that pattern better. But nothing's perfect, right? This part of the periodic table is 2 columns wide. And that's not a coincidence. That corresponds to the s orbital holding 2 electrons. This part of the periodic table is 6 columns wide. It's not a coincidence. It corresponds to the 6 electrons that fit into the p subshell.
So if we were to type in valence electron periodic table in the internet, you'd probably come up with something like that?
If you typed in valence electron periodic table
Or electron configuration.
or electron configuration, and what would you get on like Google?
Picture, right?
You might get something like this, And you know, when you want more information or a different explanation, Google is great. YouTube. You can find all kinds of stuff on there. There's lots of different ways of explaining it. And maybe the way I use doesn't make sense to you, and maybe you can find somebody else that makes more sense for you. These are the period numbers on the periodic table, the row numbers. 1, 2, 3. First level is filling the first level, principal energy level. Principal quantum number 1. It corresponds to the period on the periodic table. And here, this is the second period, and here we're filling the second principal energy level of those quantum mechanical orbitals. And here, 3. And this is not a coincidence. What is just crazy cool to me is that the periodic table was set up like this based on commonalities, common characteristics of the elements, and it had this shape, and that's before they even discovered electricity. They had no idea about molecular orbitals or anything. And it just worked out that way. Well, that's because there's a pattern underneath it all, and the reason that the elements have similar patterns in their, they have similar properties, the reason that neon and argon have similar properties is because of their electron configurations. Both neon and argon have 8 valence electrons. Their last level, their valence shell, is full, and that is a significant thing. Now, helium doesn't have any p orbitals, but its valence shell is still full. And so that's why helium is over here instead of over here. Because helium is a noble gas and acts like these guys because its valence shell is full. Oxygen and sulfur do some things that are very similar, and they both have a similar electron configuration. Their valence shell is S2P4. They have 6 valence electrons, and this affects how they react with other elements. So the periodic table actually represents all these different types of orbitals. So in the blue here, these represent elements that have their highest valence electron in an s orbital. So these represent the s orbitals. Over here, the pink boxes represent the p orbitals, and there's 6, 1, 2, 3, 4, 5, 6 columns here. The d block elements, the d orbitals, have 5 orbitals. The d subshell has 5 orbitals. It can hold 10 electrons. Guess how many columns across that is? It's 10. You can count them. And so when we look at an electron configuration, we can actually read it off the periodic table. We did bromine earlier. Here's bromine. Bromine is over in the p block, and so it's going to end in p something. If we count over 1, 2, 3, 4, 5, it's going to end with p5. And that p is going to be 4 because it's in period 4. So that's going to end with 4p5. So this is column 1, 2, 3, 4, 5. That's where we get the 5. And it's 4 because it's in period 4. And it's p because it's in this p block. Let's look at calcium. Calcium is in the 4th period. 4, it's in the s block. 4s, and it's the second one over, so it's 4s2. Now, the transition metals, those get wonky. So we're going to ignore those for now. Let's look at phosphorus. It's in the p block. It's the 3rd one over, so it ends in p3, and it's 3p3. Now, if you want to look at the filling order, it's all right there in the periodic table. So this is row 1. This is 1s, and helium's over there. So 1s goes up to 2, and then 2s2, 2p6, 3s2, 3p6, 4s2. And then the one thing weird that you have to remember, this is like it sunk down. This isn't the 4D, it's the 3D. So that's a little confusing. That's 4s2, 3d10, and then back to 4p6. Oops, didn't mean to do that. I like my green finger. Yeah, so this is 4s, and then there's that weirdness. This is 3d. Did it again? I'm sick of the green arrow. And then this is back to 4p, and then 5s, drop down 1, 4d, back to 5p, 6s, and then we're going to stop because things get weirder and we don't have to go there, so we're not going to. But S holds 2, it's 2 columns wide. P holds 6, it's 6 columns wide. D holds 10, it's 10 columns wide. So if we want the electron configuration for iodine, what we can do is we can just look at we go up one row to the end, the noble gas. So it's going to be krypton plus 5s2, 4d10, 5p5. So we can actually read it off the periodic table. Some people love that. I'm one of them. I love that. Other people are like, that doesn't work for me. I'll just memorize my list of things. Question?
Explain that one more time?
Yes. Okay, so let's actually write it out. Let's do antimony. So antimony is Sb. So Sb is right here. So to write its electron configuration with the noble gas shorthand, what I'm going to do is I'm going to find the previous noble gas, which is krypton. That's the next smallest one. So I'm going to write krypton in brackets to indicate it's the electron configuration of krypton plus some stuff. So from krypton, then we need to add on the electrons here up to and including antimony. So this is period 5. So these two boxes represent 5s2. And this D block sunk down, so that's 4D, there's 10 across there. Where am I? So 4D10, and then here we're in the P block, this is 5 again. 1, 2, 3. 5P3. Does that help? Do you want to see another one? You done with that one? I'm going to erase it.
The 5s2 is redundant on all those elements.
Pardon me?
The 5s2.
The 5s2, anything after strontium is going to have a 5s2 in it, because the 5s2 fills up, and then this is 1 electron into the 4d, 2 electrons into the 4d. So this is just adding 1 electron for every box that we go over. Did that answer your question? Pardon me? Well, there's some weird guys in there. These guys do some funky things, so don't look too closely at them. I can explain them to you, but I don't know that you want me to. Okay, pick an element.
AG.
Ag. You really want me to do Ag? Let's stay out of the transition. Not an orange one. Anything else? Not orange or green. Okay, pink or blue? Which one in the pink? Lead. Okay, I'm sorry. I heard PP. Which tells you, yeah, that's not. Never mind. Okay, PB, lead. Okay, lead. So we're going to go back up here to xenon. We're going to We're gonna run into the F's here, which is not, well, we'll just go there. Okay, we'll just go there. So lead, PB, peanut butter. Couldn't have peanut butter sandwiches for breakfast because we're out of bread. Xenon. So that resulted in a stop at the convenience store for chocolate chip cookies for breakfast. For my son, not for me. Okay, xenon. And then what's next? 6s2. And then there's 5d10. Now, what's going on here? There's a gap here, and this arrow. There's actually the F's in here. Okay, because these numbers don't work out, do they? 57 to 72. We can't ignore those guys. I won't ever have you do these on an exam or anything. 57, 58. So we have to include those. Those are the 4 F's, and there's going to be 14 of them. I cannot see this. It is way too small.
Okay, where'd you get 14?
Where did I get 14? Because there's 14 in there.
So it drops again.
Yeah.
Go into the transition line.
Yeah, this spot right here, really we should take a pair of scissors and cut this apart and squeeze these in here, and there'd be another drop down section like there is here. These elements, though, are very unusual, and that would make the periodic table far too wide, and so we just cut them out and stuck them at the bottom. So, back to this. So 4F14, we were going across here. This was 6S2. This is 5D, but then there's this thing in here, so we had to include that. And we finished up the D, and then we're back to 6S2.
This K.
Yes.
So we can only do this configuration with this table?
Well, this table has the electron configurations written on it,
So
but this table has the same pattern. All the
so we
periodic
have to
tables.
figure out the electron configuration first, then go back and write the outer electron configuration from that. You see what I mean?
The outer electron configuration, if you're just looking at valence electrons,
Yeah.
then you get to ignore these guys in the middle, because those are never valence electrons.
But without this table, we would have to write the original electron configuration.
Yeah, if you had no periodic table, you'd have to write the whole thing out to see what the valence electrons are. On the periodic table, though, like this one does not have all that stuff written on it. But antimony, it's these 3 electrons here from this group. We ignore all those guys and the 2 over here.
So
And that's why it corresponds to the number of the group number when you just number 1, 2, skip those guys, 3, 4, 5, 6, 7, 8.
So what I'm at, I don't know if I'm the only one who doesn't get this, but could you show us an example of how to find it off of that periodic table without the configuration?
Yes. Okay. No, that's good. So, yes, I screwed up here. That's 6p2. I don't know. Anyway. Okay, so the number of valence electrons for any of the main group elements except helium, because he's little and he gets away with stuff, is equal to the group number of its columns. And this is using the current US usage of group numbers, 1A, 2A, 3A through 8A. And the reason is that the first 2 columns correspond to those S electrons, and the last 6 correspond to the P electrons. And so that's going to be the highest occupied shell, and that's the number of valence electrons. The row number is going to tell us what the highest principal shell is for those valence electrons. So as you go down the left side of the periodic table, if you look at chlorine, its valence electrons are in the 3rd principal energy level. A little hard to talk about this without well, here's a periodic table I could use. So if we look at arsenic, Arsenic is in group 5A. It has 5 valence electrons. Right here, arsenic. 5 valence electrons. There's these 3 here, and these 2 over here. And they are in the 4th level. These guys don't count because they're in a lower level, a 3D level. Boron, how many, oops. Stop it. How many valence electrons does boron have? 3. How many valence electrons does strontium have? 2. How about xenon? 8. Okay? So it's just the group number. And being able to identify number of valence electrons is much more important than being able to do electron configurations. So those valence electrons are really important. The transition series, those transition metals in the middle, that represents filling up of the core orbitals, because that's not the highest principal energy level. And so the number of valence electrons for those transition metals is relatively constant. It's usually about 2. It would be the S electrons, but there's 2 exceptions in that first series. And I mentioned this because half-filled and completely filled D subshells are particularly stable. So sometimes you'll get only 1 valence electron because an electron will move up from the S room to the the D room, because there's a bonus, and so it ends up being overall cheaper. So just be aware there are some exceptions in there, and don't be bothered if we come across them. And the principal quantum level of those d orbitals is 1 less than the row number. And I think of it as being, it just sank down. They built it on unstable ground and it sank down. So these guys, they're just kind of sunken. So this is the 3D level. It's in row 4, but it's the 3D. Row 5, this is 4D. 6, this is 5D. Okay. And I kind of jumped ahead and already did this, but write the electron configuration for an element based on its position in the periodic table, looking at phosphorus. So here's phosphorus. The inner electron configuration can be represented by the previous noble gas. So neon, let's see if I can write. So neon is the previous noble gas. And then, following this arrow, what's after neon? Well, this is the 3rd level. There's S. There's 2 there, so that's 3S2. And then over here, this is 3P, 1, 2, 3. So 3S2, 3P, 3. That's the electron configuration. And that's how you can do it just looking at the periodic table. So there's still understanding that is involved. But I think it's simpler because it's just kind of, I'm a visual person. I like to be able to see things. And the periodic table makes me feel like I'm seeing it, even though it's just, I'm not. So this is kind of instructions on how to do that. Represent the inner configuration with the previous noble gas in brackets, and then figure out the outer electrons and the highest quantum number, blah, blah, blah. You can read that. May or may not be helpful. Let's do another example. Using the periodic table, determine the electron configuration for tin. Well, first of all, what's the element symbol for tin? SN. So we got to find that. There's SN. So previous noble gas is krypton. So we'll put krypton in brackets, and that is this guy, and so then we have to figure out what comes after. Well, here's 5, this is 5, S2. Yeah. S2. And then this part is D, but it's 4, right? It's sunken. 4D, and that's all full up, so that's 10. And then this is back to 5, and there's 2. It's the second one over. So 5P2. Yes.
So why on this one did we use the D block, but when we did the example of selenium, we didn't use the D block?
Why are we using the D block on this one, and we did the example of selenium and we didn't? Because when we looked at selenium, we were only looking at valence electrons.
Oh, okay.
So if we're looking at valence electrons, the D block is always going to be on the inside, part of the core. But when we're doing the whole electron configuration, we do look at the D and the F blocks. It's a good question. Anybody else?
So tin would have 4 valence electrons.
Pardon me?
Tin would have 4 valence electrons.
Tin would have 4 valence electrons, yes. Because the highest shell is 5, and there's 2 S's and 2 P's. 2 plus 2 is 4. Also,
And that's about 4.
it's in group 4A. So that is definitely the simplest way to identify number of valence electrons. And that'll be really important for our next chapter.
So when we are doing the electron configuration, will it always be D10, but then whatever group it is?
It will, for main group elements, it will always be D10, because once you get over here, that D is full. If we do these guys in the middle, if we do a configuration for a transition element, then no, it will not be D10. But once you get past that, it's going to be D10.